Welcome to EET3329C Communication Systems at Valencia College for the fall semester of 2020. This is your lecturer, Dr. Wilfredo Rivas Torres, and this is our lecture number 3, part 3. And this will be the last part of lecture 3. It had a total of 3 parts, and we are talking about analysis and transmission of signals. In, in part 3, what we're going to talk about is signal energy and energy spectral density, the signal power and power spectral density, and finally, we'll talk about the discrete Fourier transform and how we will implement that in our computer program, Octave or MATLAB, using the FFT, which stands for the fast Fourier transform. Signal energy and energy spectral density. Um, so you have a signal, a real signal GFT, and we know that the energy is the area under uh, the graph squared, or the waveform squared, right? So we can determine the energy also from its Fourier transform uh, through Parseval's theorems. Parseval lets us do that. So thanks to Parseval, we know that if you have, in general, a complex signal, if you do G of t times complex G of t, that'll be equal to doing capital G of f times capital GF um, conjugate, which is the same as doing the magnitude of your complex signal squared, uh, integral over frequency. So this allows us to determine the signal energy in either domain. We can be in the time domain and the frequency domain, and typically it depends on the information that we're given and which expression is easier, right, for us to integrate. Here's an example. It's from our textbook. To verify that Parseval's theorem with the signal g of t equals e to the minus at u of t for a greater than 0, right? So I think we've done this kind of exercise before, but just to refresh everybody, this is a real signal, so we just square the signal. It's times the unit step. So the unit step is 0 before t equals 0, so we can change the limits of integration from 0 to infinity, plus infinity. And if you do that, you end up with a result of 1 over 2a. Now, if we look for the Fourier transform of g of t, we have that g of f equals 1 over j pi f plus a, right? If we square that, right, to do the energy in the frequency domain, we square that, and uh, you can go and look in an integral table and you find out that, oh, this has the shape of the inverse tangent um, result for the integral. And then when you evaluate this from minus infinity to plus infinity, you also end up with 1 over 2a, right? And this satisfies Parseval's theorem. Now, the energy that we calculate is contributed by all the components inside the signal, right? So the spectral components of the frequency um, at any frequency are proportional to the square of the spectral uh, result, right? Or the Fourier transform squared. And then I guess to say the Fourier transform magnitude squared. Okay, just to be correct. Now consider that we apply GFT to a bandpass filter, right? Who we know has a transfer function h of f, kind of as shown here. Notice that a bandpass filter only occupies a certain delta f in the frequency domain. Okay, so it's like our square pulse magnet, height of 1, and a certain width delta f. Remember, this will suppress all frequencies except those frequencies that are within our range delta f. Um, if we call the output of the filter y of t, then we know that y of f is G of f, Fourier transform of the input times the Fourier transform of the transfer function, right? In this case of our filter. So the energy is nothing but the y, right? Whatever y is, which in our case is g times f squared, right? And we integrate over the frequency. Now, because we know that the magnitude of h of f is 1 over this narrow bandwidth, we only really have to do that integral over this narrow bandwidth. And if you do all that, you end up with E of j equals 2 times whatever G of f centered around f0 is, right? Times delta f, right? So you just need to figure out, and this is your G of f, right? You figure that out. And then you just multiply G of f times delta f, and you have a good uh, measure of your energy. Um, Now we can continue to make delta f relatively small, right? That's why we say, oh, as we let delta f tend to 0, right? And then in reality, this energy ends up being an energy spectral density. So it's going to have units, right? If we're talking about energy, let's say joules, is going to be joules per hertz, okay? So it's a density, it's a spectral density. And whenever you talk about spectral density, be energy or power, it's on a per hertz basis. Okay. Um, Now the spectral the spectrum of many signals is infinite. It goes on forever, right? It can, as you go to infinity, it will begin to approach 0. You go to f of tends to infinity, right? Now, we normally don't really deal with infinity quite well, and for all practical purpose, and we're talking about signals, there's a point in the signal where uh, after that certain frequency, the energy that's contributed is fairly small, or we could call it negligible, right? Um, so what we would like to do is find that bandwidth after which the signal has negligible energy, and we'll call that our essential bandwidth, right? And let's say we have a measure. This is by no means a standard measure in the industry or anything like that, but some people like to think about it this way, right? Let's say you look for the 95% of the total energy, right? As long as you find what that delta F is or this bandwidth, you say that that's the essential bandwidth or the bandwidth of interest. And essentially, what we're saying is if we frequency limit our signal, remember earlier on we were saying, oh, if I want to make a signal causal, I can limit it for only for t greater than 0. Well, think about the same thing kind of concept, but now we're doing it in a frequency way. So we're saying it goes from frequency f1 to f2, that's our essential bandwidth, and we're done with it. And if I took um, that spectra and I did the inverse Fourier transform, I'm going to end up with a signal that let's call it g hat of t, okay, which is a close approximation of our original g of t, okay. In fact, if you want to use a criterion, right, a criteria, if I take g of t minus g hat of t and I measure the energy of both of those signals, I should get an error of about 5%, right? Because I said 95% is my criteria, so the error is 5% in the energy, okay? And let's say the 5%, we say that's negligible. It, it really depends on what you're doing. So here's an example from the textbook, right? It's example 320. Um, so we're going to use the 95% criteria with the signal of our prior example. It's e to the minus at u of t. So this is my signal g of t. And what we're looking at for the essential bandwidth. And again, the author does this thing where they're mixing omega and 2 pi f. So hopefully you guys don't get confused by that. Okay. So this is g of f, right? The magnitude of that is just you square that, right? Magnitude squared of of that is this expression, which we saw before. And what we want to do is, hey, I want to say I want 0.95 of that. What would 2 pi f or w have to be, right? So we know how to solve this. We did a little while earlier, right? So we're looking for this w, right, divided by 2 pi, which oddly enough is f because we are integrating over f anyway. Um, and we end up with this expression. Okay, I'll let you guys walk through the integral. And then you have 0.95 pi over 2, right? Um, okay. So the author got already simplified this expression, right? He's saying 0.95 to a equals, and he got rid of the a because, and then this is why there's a pi there. Okay, I got it. So that's going to be inverse tangent of w over a, and so w ends up being 12.7 a radians per second. And we always like to convert this back to hertz, so frequency. So we take that the w that we got here and we divide it by 2 pi, and it ends up being that your essential bandwidth is 2.02 times a, or 2a. Let's just go ahead and round it off. And so with 2a, you get 90%. With a bandwidth of equal to 2a hertz, you get 95% of the energy contributed. Okay, so if we could design that brick wall filter, I would design it to have a bandwidth of 2.02a, and I would capture 95% of the energy in the signal. That's another way of looking at it. Um, so let's talk about energy of modulated signals, right? So let's say you have a signal at baseband, let's call it GFT as we've been calling it, and we are going to band limit it, right? So when we look at it in the frequency domain, you have a signal like this, and it goes between minus B and plus B, okay? We know that our modulated signal, let's call it phi of t, is equal GFT times the cosine, where this is the carrier. You guys remember that? And this is the Fourier transform, which we've also seen before. And this sort of looks like this, right? Um, well, no, hold on, hold that thought for a second. Um, it kind of looks like this, but this is representing something else. So the energy spectral density of phi of t, right, is what we're going to call psi of f. That is 1/4 of this multiplied square, which is we're just taking the Fourier transform and we're squaring it, right? So we take this expression and we square it, and that's actually what we're showing here. Sorry, I got a little ahead of myself. So this is the energy spectral density of the input, and notice that when you modulate it, it just sort of uh, frequency shifts it plus or minus f0, okay, wherever the carrier frequency is. We can also talk about the energy spectral density of an LTI system. Again, the same sort of concept. You just need to square the output, right? Which means if I want to square h of f times x of f, that's our result here. So um, we also know that x of f squared is the energy spectral density of the input. So we can say that the energy spectral density of the output equals my frequency response squared times the energy spectral density of the input. Okay, and this is true for any LTI, linear time invariant system. Signal power. We're going to see that signal power borrows a lot from what we just did for energy. Remember that signal power is nothing but the time average of the signal energy, right? Um, so we can, let's say that we have some signal GFT and that we're going to truncate it between uh, T over 2 minus T over 2 and T over 2. So originally this was our signal, and then we're just going to truncate it to a certain period of time. Okay? This is what I was just saying. The power is nothing but the time limit of the energy over a certain interval of time, that in our case is called T. Um, And we can also talk about the power spectral density, or PSD. And this is more common. In practice, we talk more about the power spectral density than we talk about the energy. Okay. And we'll define the power spectral density as the limit as t goes to infinity of, again, the magnitude square of our frequency spectrum divided by t, whatever t is, right? And notice that we want to let t go to infinity, okay? Um, Another way to calculate power, if you happen to know your power spectral density, you can actually integrate it, right? And you get the power in your signal, okay? Um, if the power spectral density is typically is a an even function, right? So you can just integrate from 0 to infinity. And that's sort of what's inside this box. And this is what we're trying to tell you. Um, since the power spectral density is really a time average of your energy spectral density, we can argue along the lines used for ESD, right, for the energy spectral density. Um, And we can actually say that power spectral density represents the power per unit bandwidth. It's a density. I already argued this with you guys, right? So I said that everything in here, when you talk about density, is per something. In our case, it's per hertz. Okay, so we can talk about what is the amount of power within a certain bandwidth, or within between two frequencies, right? Within certain some people will call it band or bandwidth. Um, so from F1 to F2, if I integrate that, multiply it by 2, I know how much power is contained in that bandwidth, right? And really, this is one of the biggest uses of power spectral density is right here. Okay. Um, the same sort of relationship between the input and the output that we have for energy spectral density for linear time invariant systems. So we know that the output power spectral density is going to be the transfer function squared times the power spectral density of the input. Um, Here's an example from the author, and it's a good segue into talking about noise. We haven't mentioned noise in a while. So noise, right, we said before when we talked about the additive Gaussian noise channel, right? Um, we said that it's white noise, so it's the same value from minus infinity to plus infinity, right? Um, but in this example, we're actually going to band limit it. So let's say we know we have a certain noise with um, a value of k, right? And we are going to band limit it between minus b and plus b. And we want to determine the power spectral density and the power of the output noise signal of of our system here. We're going to start off by assuming that we have an h of f. Oh, I'm getting a little bit ahead of myself. And this is going to be input into an ideal differentiator. So we're going to have a certain noise at the input, and we want to know how much the noise at the output is, right? So we know what the transfer function of this is in the frequency domain, because we know how to do the Fourier transform of the derivative, right? It ended up being j 2 pi f, if you guys remember, when we talked about the Fourier transform in the first part of this lecture. And you can always refer to that table, right, which is on slide 20 of this presentation. So if we say that this differentiator represents a demodulator, now we haven't really talked much about the demodulator, but a demodulator undoes whatever the modulator did. Remember, the modulator is the thing that multiplies our signal times the carrier and sort of takes our information and sort of shifts it in frequency. Well, the demodulator will undo that, so it'll shift the signal, our information, back to baseband, so that we can interpret what the signal is, right? So what we want to do is, what would the noise be if we know the noise at the input? What would be the noise at the output of our demodulator? Which is a thing that we do in practice, by the way. Yeah, you want your demodulator obviously to add the least amount of noise possible. So just keep that in mind. So this is a somewhat practical example. So if we know the power spectral density um, is nothing but the transfer function squared times what we have at the input, which is k, right? We said it was k, and it's band limited. Okay, so we know the power spectral density of noise at the output. Now, because we know we're going to band limit it, in order to calculate the noise power, remember we're talking about noise power, yes, this one, right? We want to know the noise power. We just need to integrate between those two frequencies. Okay, and that's exactly what they're doing here. We know what the power spectral density at the output is. We're going to integrate over frequency, and then this is your noise power at the output. Okay. Um, Again, similar concept for the power spectral density and modulated signals. So if we say this is my modulated signal, this is what the power spectral density will look like. Okay, this is the expression for it, right? And again, remember it's going to create um, uh, two what you call it, power spectral density representations that are shifted plus or minus f0. Okay, remember, it's the shifting of the power spectral density of our original just shifts at those two locations. Okay, um, so that was the end of the power spectral density. Let's talk about this concept of a discrete Fourier transform. So we've been, when we even if we go back to lecture two, when we started talking about vectors and we started about creating a signal as a vector, we were doing discrete samples. We were looking at the signal and we were just picking those samples that we wanted at certain time intervals that we call the sampling time, right? We can actually do the same thing with the frequency domain. And if you're wondering why would we do this, is like I started saying, is we want to be able to do this, programmatically in a computer, um, or in some kind of embedded system. In order to do that, we need to also discretize our, our frequency responses and our power spectral densities and all this stuff. So how do we do that, right? That's where the discrete Fourier transform comes in. We're actually going to sample it, okay? Um, so this is pretty much what the slide is talking about. We're going to try to have a finite number of frequencies. Um, and then, so our next step that we want to do is establish a relationship between the finite samples of G of t and the finite samples of G of f. What's the relationship between those two samples? Um, and we always start from where we always do. We start off from a time limited signal, okay? It's kind of hard to do if you don't have a time limited signal, right? And I know we've been doing this time limited signal for a while, but I hope that by now you guys realize that we never can deal with a signal infinite samples. We always time limit our stuff. So we always look at a certain window in time or a certain window in frequency, right? This is why we can actually do this on, uh, programmatically, again, either on a computer or on an embedded system. So let's start off with some signal, right? Some signal g of t, and we're going to say the signal duration is tau, okay? Starts at t equals 0, and after tau second, it ends. So we can look at the corresponding frequency right, response of this signal, again, through the Fourier transform, right? And this is what it looks like. And we already know, and we've been doing that for a while now, right? Now, if we're going to sample this in the frequency domain now, we have to sort of consider a certain frequency resolution, right? So frequency resolution, we never mentioned this, by the way, in the time domain, right? But when you time sample, you actually are getting a time resolution. What you're saying is that this is a time sample small enough that I capture everything that's important in the signal, right? So there's no feature in your signal that is of importance to you that is smaller in time than that sampling time. We want to do the same thing in the frequency domain. So we're saying that there's no feature in the frequency domain smaller than this that we are interested in. Okay? And so that's our resolution. It's like a picture, right? When you take a picture, your camera has so many dots per inch. That's your resolution, right? So what you're saying is, when you're talking about a picture, is there's no feature in that picture that is smaller than that is of interest to you. Okay. So now let's say also that in order for us to guarantee the frequency resolution, we are going to allow our signal to go to some duration t0 where t0 is greater than tau. Okay? And that's what this picture shows. Notice where t0 is. It's actually larger than tau. Okay? So what happens is we're going to make g of t equals 0 in an interval between tau and tau 0. Right? So this little piece of the signal that's shown in this graph, that part is of it, it's just 0. Okay? Now we can make samples of GFT, right? And we can actually make it, we already done this before. We can make our signal periodic, for example. So we can take our signal up to tau, and then from tau to tau 0, it's 0. And then we can repeat it, right? And kind of do the same thing. By the way, the whole period between all the way up to tau 0, right? That becomes the period of our new signal if we wanted to do that. Um, the fact that we extended the signal up to tau 0 does not change GFF. That's why in the textbook it says it makes no difference in the computation of GF. Okay, you can go back to the definition of the Fourier transform and prove that to yourself. Okay, now if we sample the signal, we know that there's a total of n0 samples, right? And we pick them all out, and we know that n0, again, we've seen this before, n0 is t0 over ts. So this is just the number of samples that we would have in one period of our signal, or an interval of interest for us right now. And the Fourier transform, right, because this is all discrete, now becomes this expression that we have here. Okay, everything is discrete, and we approximate, or we get closer to GFS as the limit of TFS, the sampling time, gets smaller and smaller and smaller. Okay, as it goes to 0. Okay, now let us consider. Now let's go to the frequency domain. Let's say we are going to pick up, or we're going to sample it at intervals, and we're going to call our intervals f sub 0. Um, so we can actually, so we can actually say that if I have the Q sample, G of Q is going to be Q F0, where Q is an integer. Okay, so 1, 2, 3, 4, 5 times F0, and then until you get all the samples. Which, by the way, is the same thing we've been doing in the time domain, right? It's just that we don't call it F0, or right? We call it TFS. We just did that. And then you can say that you have GQ, right? It's going to be this summation from k equals 0 to n0 minus 1 of this expression, right? Which again, we've seen before, and it looks awfully close to the Fourier series, which, right, and the way we evaluated those things there. Okay. And finally, we reach a point where we know that the G of K's are nothing but Ts times G of K Ts, and GQ is nothing but G of Q times F0. Okay? And this is the equations, this thing here is what it establishes a relationship between G of T and G of F, right? The sampled ones, okay? Between the samples of G of T and G of F. Um, Now we have assumed that Ts goes to 0. In practice, this doesn't happen. It doesn't go to 0. We actually say, oh, we're working on a system with a certain sampling time or sampling rate. Sampling rate is nothing but 1 over Ts, or this, it's a little hard for you guys probably to see here, but this is Fs equals 1 over Ts, right? If I say sampling frequency, sampling rate, I'm talking about the same thing, okay? So, okay, so it can't go to 0, but we make it small enough, right? Um, so the other thing that this equation does is it shows that GQ is also determined by N0 independent values. Isn't that interesting, right? So notice, and the reason we say that is because we did our summation up to N0 minus 1, all right? So that is quite interesting, that GQ and what you call it, our GKs are related through N0. That means they have the same number of samples too, right? Um, this also means that F0, right, that frequency resolution that we were talking about, which is how we're going to sample the frequency domain, is actually 1 over T0. So remember that T0, that's the period of our signal, right? That's the period of our signal. And that actually becomes your frequency resolution or your spectral sampling frequency, right? Which is a remarkable result, by the way, right? And now you can see how the frequency domain and the time domain are linked through all these values, okay? So if you want to, so the spectral sample frequency can be reduced by increasing T0, right? Um, So decreasing F0, right, yields more details of GFF. Remember, we want to have a F0 so that it resolves down to the smallest frequency detail that is important to us. Okay, that's our resolution. So really what this comes down to, the DFT really comes down to, is a choice of our sampling time, our period, and number of samples. And we know that these three things are related to each other. And we know the function, right? N equals T0 over Ts. We saw that just a minute ago, right? So how do we determine what are the right values? Well, we first start with an estimate of B. Remember, B is that essential bandwidth that we were talking about just a little while ago. So the essential bandwidth to us, right, comes comes straight from here, from our original signal. So if you select an f of s such that when you look at the frequency domain, and if if the spectral is going to repeat, and it does, right? When we do the DFT, what ends up happening in the frequency domain is these things repeat each other. It repeat every certain amount of time. What time is that? The sampling frequency, which is 1 over s, 1 over ts, excuse me. Okay, so if the bandwidth of your signal, right, the total bandwidth of your signal is greater than f of s, what happens is these things in the frequency domain begin to overlap, and we call that aliasing. Okay, and aliasing is not a good thing. You actually want to avoid aliasing. Now, how much aliasing and where does that, where there's this crossover, I'd like to call it a crossover point, or spectral overlapping point, right? Uh, you can see why I call it crossover, the spectral overlapping. Okay, so What you don't want is this one to overlap with that one. If you can keep them separate, that's an ideal world, right? So that puts a limit on what f of s has to be. So if you know the original essential bandwidth, your f of s has to be at least twice of that, right? Okay. And that's what we're saying here. If GFT is band limited, then clearly its bandwidth is identical to the essential bandwidth. Hence, f of s has to be f of s over 2 has to be greater than the bandwidth, which is the same to say that f of s has to be greater than 2 times b. Okay. Um, and that's what we're showing here. F of s has to be greater than 2 times b. And since the sampling time is 1 over fs, that also means that ts has to be less than or equal to 1 over 2 times the bandwidth or the essential bandwidth. By the way, f of s set this way is what we call the Nyquist theorem, uh, the Nyquist rate. Okay? So what Nyquist says is if you sample at least at fs 2 times your essential bandwidth, you can always recuperate your signal back, right? Your original signal back. Um, I am not being very rigorous. So those of you who have taken like a signal processing class, and those classes, they should go a little bit more rigorous than what I'm doing here. But just know that your sampling frequency has to be 2 times the bandwidth or greater so that you can always get your signal back when you go back from the frequency domain to the time domain or whatever it is you're trying to reconstruct. Okay. Also know that your resolution, your frequency resolution is 1 over the period of whatever the signal is. So whatever sampling uh, time you select, notice I was careful not to say sampling period, not to confuse it with TFS. So whatever sampling period you take, right, that will be your frequency resolution. Um, so if you know your f of 0, right, your frequency resolution, you can always pick T of 0, right? And then knowing T of 0 and T of S always tells you what N of 0 is. So really for the DFT, this left-hand side of this slide is what's really critical and probably worth um, sort of making yourself a note and probably keeping keeping this as a reference. Um, There's some more detail here. If the signal is time limited, then GFS is not time limited, and there will always be aliasing. Okay. To reduce the aliasing effect, we need to increase the folding frequency, okay, or the transition frequency, um, to avoid that. So that means reducing T of S, or just go ahead and band limit the signal. And really, the way that we control aliasing is we don't, you know, there's a in every system there's a practical limit to how small you can make your sampling time. So unavoidably, we end up band limiting the signal by uh, filtering it. We put it through a filter, and a filter will have a finite bandwidth, right, that we can talk about. Let's say it's the 3 dB bandwidth, which is half the power, and not the 95% that we were talking about, right? It's 50% in this case. But let's say that that's what's important to us, right? It could be bigger, it could be smaller. It all depends on what you're doing. Um, um, so yeah, that's about as much as I wanted to say about these other points. Okay, so remember, you can reduce TFS up until to the limit of whatever system you have, right? Whatever sampling frequency you can muster up. And you always want to filter your signal before you go into it to whatever bandwidth you need. And from now on, we can call that the essential bandwidth. Now, the FFT. So how do we do these? discrete Fourier transforms, right? Again, on the computer, on our embedded system. Um, Now, if we were to just do the DFT, which we can because there's expressions for it, and we can definitely do that. And we know how to pick up samples from signals, and the spectrum is no different. We can pick up samples from that, right? But it really becomes, depending on what N0 is, and depending on your frequency resolution and all that, this can be fairly time consuming, right? Even on a computer, right? So back in 1965, Tukey and Cooley came up with an algorithm that is known as the fast Fourier transform. In practical terms, right, if you just want to calculate the DFT, you end up having whatever N0 is, right, which is the number of samples, square that, and that tells you about how many computations you have to do to calculate the DFT. Well, what the FFT does, it reduces that number to something n0 log of n0. Now, if you calculate n for any n, square it, and then for that same n, calculate n0 log of n, and you'll see that this n log n value is always less than the n square. So, and the larger the n, the bigger the savings in computation time. Um, there is a well-known uh, um, fact. There's a well-known fact about the FFT that if N0 is a power of 2, it sort of helps or simplify the FFT algorithm, and therefore it goes even faster. Okay, so FFT, if you can make it the number of samples power of 2, right, like 2 to the 10, which is 1024, right? That makes the FFT go faster. Okay. But in general, that's not a requirement. You can act on FFT of any size, and it's still faster than calculating the DFT. Okay, having said that, let's do a few uh, octave examples based on the FFT, actually. So we're going to start off with our now famous exponential times U of t, but this time instead of making it generic with A, we'll just say e to the minus 2t times U of t. Now let's do a little pre-work, right? So if I say, we already know that the Fourier transform of this is 1 over j 2 pi f plus a, when in our case a is 2, so that's plus 2, okay? Um, so let's say we're going to band limit this and that we are interested in the frequency where the signal drops to 1% of its peak at 0, okay? Furthermore, if we say that 2 pi f is much greater than 2, looking at this denominator, right? If that's much greater than 2, then this f is no longer that critical. It contributes very little, and this whole thing becomes 1 over 2 pi f. All right, so that becomes the magnitude. All right, and we're going to assume that 1% is at a frequency where we can make this approximation. Okay, so if we do that, then we can say that 1 over 2 pi b, which is the frequency that we're interested in, right? That would be our essential bandwidth, is going to be half, right? Because this, if you evaluate this at 0, right, we want it to be 1% of what f is at 0. If you evaluate this at 0, right, this whole thing goes to 0, then you're left with 1 over the square root of 4. Square root of 4 is 2, so you end up with 1 over 2. That's where the 0.5 comes from. So we're going to say 0.5 times 0.01, which is 1% of value at, at the frequency at 0. So we end up with a b that equals 100 over pi. Now, we said that we want the sampling time to be less than or equal to 1 over 2b. So it ends up being 0.005 pi, which is 0.0157. So now we know our TS. However, in this example, the authors go and say, well, why don't we round this up to a smaller number? Remember, and when it comes to sampling, smaller is always better. So they come up with this number 0.015625, which happens to be 1 over 64, right? So that means that at every second, we're going to have 64 samples, okay? Um, so we say that we have a sampling frequency of 64 hertz, right? Uh, the second issue that we have is now we have to calculate T0. So the signal in reality is not time limited, so we need to truncate it somewhere, right? So the author wants to make sure that GT is much, much smaller than 1, and they say, hey, let's pick 4 seconds, which is eight times the time constant of the signal. That's okay. I think we can live with that, right? Um, and if we do that, you end up that N0, which is T0 TS, is 256, which conveniently is a power of 2. Okay. Um, Now the author does this a lot. Um, and what they do is anytime you have a discontinuity, and I discussed this in an earlier example, I think it was on lecture 2. Whenever you have a discontinuity, right, like pulse or the U of t function, right, which we're using here, at t equals 0, what do we do there? What is the value of the signal at t equals 0? How do we do that? Because you have to think about this for a second, right? Right before 0, at that infinitely small interval, right before 0, the signal is 0, right before t equals 0. And right immediately after t equals 0, or at t equals 0, the signal is 1. In the real world, you never have that. Plus, that's a discontinuity. If you try to do the derivative of that, it goes to infinity. So it means that, we don't know what to do with it at the end of the day. In the real world, that never happens. The signal actually always has what we call rise and fall times. And it takes the signal a certain time to get there, right? To go from 0 to 1, right? And by the way, that's also due to causality. You really can't go from 0 to 1, right? No signal, all of a sudden having a signal at the output, right? That jump is not realistic or physically possible. All right. So what we aim to do is repeat the results of the book. So the book, what it does is calculates the actual DFT, which is the solid line, and the sampled ones. And it does it for both the magnitude and the phase. So let's go ahead and look at octave and see how that is done. Okay, so here's octave. And I did, and in this example, I follow the author quite example from the textbook. And you'll see in the next two, I will not do that. But in this one, here's our A equals 2. We said the time sampling is 1 over 64, and T0 equals 4. So this comes straight from what we saw in the book. Now, in the book, when you look at the example, they put a lot of these commands, one next to the other, and on the same line. I sort of undid that for clarity. I understand why they do it on the book, right? They want to save space in the book. But I think this putting them in a more sort of one instruction per line makes it a little bit more legible for you guys. All right. So notice how we calculate N0 is nothing but T0 over TS, which we specified. And then here's our vector T, right? From 0 in increments of TS. And then we're going to go to TS to times N0 minus 1. Okay. And if you do that, you end up with T having N0 samples. Okay. Here's G, right? And then here's the fix that the author does for that discontinuity at 0. What they do is they say, what is it, the signal immediately before 0, and what is the signal immediately after 0, and they do an average. So from 0 to 1, you have two values. You divide it by the number of values that you have, right? N in this case would be 2. So 1 divided by 2 gives you 0.5, or midway between those 2 points, right, between 0 and 1. If the value were 0 and 5, you would say 2.5, okay? And if you do that, everything actually works, and everything that we referred under the theory works, right? So we have the sample vector G for our signal, right? We fixed our discontinuity at 0, and then we calculate the DFT using the FFT, okay? There is this function, Cartesian two-polar. You only do that because you want to have G of P be the phase and G of M be the magnitude. Okay, so that's what this function does for you. It takes something that's real and imaginary and it converts it to magnitude and phase, right? Because we want to plot the magnitude and the phase. That's all. You do have to come up with a frequency vector so that you can plot the magnitude and the phase versus frequency. Notice that it has n0 uh, samples, as we said in the theory when I was talking about them in the slides. And you just establish this k vector in order to do that, right? So instead of doing it like the way we did it with t up here, right? We're going to do it this way. Hopefully you guys can follow that. And then uh, I'm not 100% sure, but then again, here's the author doing it with omega, right? Why would the author wants to go to angular frequency? Again, I really don't know. I sort of saw the calculation. I'm showing it to you guys, but I'm not going to use it. Okay, so notice that I don't think the author does either, by the way, but they did calculate it. So I just wanted to be thorough and follow the examples fairly close. All right, so here we're going to plot the samples. We use the stem function, right? The stem function lends itself just to plot samples, so you can see the samples where they are. And horizontal will be f vector. Now here's a curiosity. Uh, if you notice, we know that n, right? We know that we are going to end up with 256 samples, right? We sort of knew that, right? But the author does not plot them all. He only plots between 1 and 32, okay? And that's just because it's enough, right? We could have plotted more if we wanted to, or we could have plotted them all, okay? There's no good reason to do or to not do that, okay? Um, and then the rest of it is just putting labels and the grids on the table, on the graph, excuse me. Also, what we're going to do is we are going to plot the phase as well, okay? So here's the thing where we plot the phase. Here's a G of P, okay? G of P times the frequency vector. And then after that, the author actually calculates the same thing, but this time using the analytical results. So the 1 over A plus J 2 pi F, right? That's, you can see it right here. Here's the theoretical G of F. And again, we do the same process again. We use a Cartesian two-polar to get the phase and the magnitude, and then we plot them again. Except that this time for the analytical one, we won't use stem and we'll actually use plot. So we want a continuous plot. And actually, if you run this, and again, you guys in the class do have this, I did upload it to Canvas. Let me bring it into full view and let me make this a little bit bigger. Okay. And then you see that the line, right? That's a theoretical one, and you can see where we're sampling um, the one with the FFT. Okay, and the same thing happens down here in the phase plot. Okay, um, so nothing really super fancy about this example, other than we made a conscious effort to make sure that we understand what TS, T0, and N0 is. And we also showed you guys how to use the FFT, right? Once you have your samples, it's just the FFT of, of your signal vector. Okay. All right, this is another example from the book. They want to use a DFT implemented by the FFT to calculate or compute the Fourier transform of eight times the pulse function, right? And then we want to plot the resulting spectra and compare against theoretical values. Now, if you look at the book and you look at my results, they're different, right? And the big difference is I did not take care of the discontinuity in the same way the book does. Now, we will talk in a little bit why that is. Oh, before that, let's go to Octave. Hold on. Now, for those of you in the class, you'll notice that my code is shorter than the one that the authors have, right? Again, I did not take care of the discontinuity. Not having to do that makes the code a lot lighter, right? I'm gonna first run it to show you guys the results, right? First of all, this is the samples of the signal, right? And the author goes on to say that they're doing everything for t greater than 0. So the points that would have been at the minus time or time before 0 actually end up being on here on the right side. Okay. Now, if you notice, if you look at this closely, then there's two discontinuities. There's one here after the fifth sample, right? So in all honesty, I should have made this fifth sample half, and the same thing with the first sample over here, um, close to 3.5, right? At 3.5, I should have made that a half. I did not, because in the real world, right? First, this phenomena doesn't happen in the real world, and number two, if even when the signals are really fast, right? And sometimes they are really fast, there's still going to be certain filters and there's going to be certain frequency responses that are actually going to sort of spread the energy anyway, right? We kind of saw some of that when we talked about LTI systems. So while the example and the way the authors do it is 100% valid and correct, okay, I chose to not do that to show you guys if you were to actually sample something like this in the laboratory and you took those samples and you did the FFT of that, what would you get, right? You're not going to get the exact same sync function that the authors got, which is, again, totally correct and accurate. You're going to get one that kind of looks like this. Now, it's really hard to see it, but hopefully you guys kind of begin to see um, this point should have been 0, but there's a little bit of component there, and the same thing happens here, right? Some of these components, just the magnitudes are totally different, again, from what the authors have, right? Because again, I did not take care of the discontinuity. So it would look different, right? So if you ever want to take samples in the lab and you get something that looks like this, right? Just know that you have to take care of the discontinuity, or before you do that, just go ahead and probably apply some filter, and that'll sort of soften this up. It does spread it, but it takes care of it, and it's more realistic. And if you ever see something like that, okay. So talk a little bit about the code. Here's that rectangular function. There's different ways to do it. I chose to use, we have a rectangular pulse, right? So if I do rectangular of t over tau and rectangular of t minus 4 over tau, I get the same uh, square waves, if you will, that the authors have. Um, we then create the samples, right? And then we just evaluate GTD based on our samples. Nothing different from what we did in the prior example. And then we plot it. The one thing here is right? Or there's a couple of things here. Um, so I should have probably separated this for you guys in the class and put a note here that this is where we're doing the DFT, right? So here I'm calculating what the frequency resolution is going to be. And then based on the frequency resolution, since I already have a vector k, and I know that I'm going to have that same amount of samples in the frequency domain, and I know that what the frequency resolution is, okay, I just create my frequency vector as k times f0. Now, let me explain this b in just 1 second. I'm going to come back to it. When I calculate the FFT, right, there's the calculation of the FFT. The FFT doesn't create the frequency spectrums in the way we're used to looking at them. So we always look at them as from with frequency of 0 in the middle, and then we see the negative frequencies and the positive frequencies. Well, the FFT doesn't do that. Doesn't like it or it's just the way that it got developed. The FFT keeps everything in the positive frequency domain. Okay. Um, But that's not, we already know that that's not correct. We know that that second half really belongs to the one that's going to repeat. Remember a little while ago I told you when we were looking at the DFT that the spectrum sort of repeats itself when when you're doing that, right? So we're really looking at the second half. If you don't want to do that, looking at the second half, and that's problematic, right? And in most cases it is, to be frank. What we do is we shift it. And that's what this FFT shift function does. It just takes that half that's, you know, should have been part of the next sort of spectrum, and it flips it over and it puts it on the negative frequency side. The thing is, our vector had started at 0, and because I continue to want to use k, I then used b, which is my essential bandwidth or my Nyquist rate, right? Excuse me. My Nyquist rate is based on my essential bandwidth, right? With this 2b. So if I subtract b, which is 4 over tau in our case here, that's what we selected. And if you read through the example in the book, they kind of justify the 4 tau. Um, and then that's it. Um, you can plot this and you get the plots that I just showed you a little while ago, right? Okay. Now, I have a third example for you guys. This one is not in the book, but it's a continuation of the one that we just saw, sort of. So instead of using the rectangular pulse, I am actually going to use a square wave. And we're going to, for the square wave, I am going to use the EFT, or calculate the DFT using the FFT. And then we're going to take our bipolar square wave, and I call it bipolar because it doesn't go from 0 to 1. It goes between 1 and -1. And then we're going to do the Fourier transform of that again, right? But after we filter it. So let's look at this and kind of what we got, kind of see what we get. Okay. All right. So here's the octave code for it. Um, I selected a sampling rate of 50 milliseconds, right? And if I have a pulse or signal with a 1 second period, 50 milliseconds gives me like 20 samples per period. I think that's good enough. I'm going to say T0, so it's going to be 5 seconds. So I'm going to let the signal run for 5 seconds, and I can calculate N0. Again, B is going to be, actually this is FFS, but here I accidentally called it B. But let's just go ahead and roll with that because I should have called it FFS. Sorry. And then here's K as we did before, and here's our T vector. Our signal, I call it GTD, is the square function. You do have to load the package, load the signal package if you don't have it loaded for the square signal to work. All right, that's at least true in octave. So the first thing I'm going to do is I'm just going to plot my signal, right? Here's my vector with the samples on my signal. So I'm going to just go ahead and plot that. And then I am going to the same thing that we did before, and I am going to calculate the FFT, right? And I'm going to shift it so that it looks the way that I expect it. All right. Um, I said I was going to filter it, so I'm going to go ahead and use a filter, the FIR filter. It's called FIR1. And you give it a normalized frequency. What is a normalized frequency after all? Well, what you do is you take your frequency of interest, right? This is going to be the bandwidth of my low pass filter. I'm going to make it 5 hertz. And then you divide it by f of s, or your sampling frequency. And again, I apologize for calling it b. I um, that was not intentional. Okay. So anyway, um, just okay. So the next thing is we need to calculate the impulse response of our filter, right? So I'm going to use this FIR1 function, which is what's known as a finite impulse response filter. Again, those of you who've taken the signal processing class know what that is. So I'm going to calculate the impulse response of that, and then I'm going to convolve it, and that's going to become my new GFT. So my original GFT was just a square wave, and then I'm going to filter it, and then that's going to become my new GFT, right? And then I'm just going to repeat the same process. Luckily enough, right? Luckily enough, all these equations just look very similar to what I did before. So I'm going to have the FFT, I'm going to shift it and everything else, right? Then I just going to plot it. So let's go ahead and look at this. What do we get? And what do the results look like, and what can we say about those? Okay, let me bring up the graph so you guys can see it. All right, so there's more to come in this example. That's why there's some white space here. But let me see if I can stretch this out for you guys a little bit more. There we go. So upper left hand side of of here, that's our square signal. You can see it. Its duration is five seconds, right? And if I do the Fourier transform, and I am only looking at the magnitude. I neglected to say that in the code. Let me go back real fast to the code and show you guys that. So I did the FFT, and when I went to plot it, notice how I do ABS of GQ. ABS stands for absolute, or the absolute value or something, which if it's a complex number, it gives you the magnitude. Okay? So going back to the graph, this is what it looks like, right? So it really does have a sync function to it, but because I'm not looking, I'm looking just at the amplitudes. Even if it's negative, it's going to show it as positive. But you can see how it alternates and goes and kind of sync like, but not exactly, right? Now, the one here in this is actually the middle. Okay, again, the signal lasts from 0 to 5, but all of a sudden we see something uh, different, right? The signal does not look like like the original signal, right? Um, and this is just some low pass filter created by the FIR function, right? Um, now, if that FIR function is an LTI system, right? It should look, the signal should look similar in shape to what I look at the input, and it does, and it's similar in shape, right? But we already know that it's going to do a couple of things. One, it's going to create delay because causality imposes that to us. And sure enough, look, the signal at the beginning, there's kind of nothing there. Then you kind of see it with little waves, and then all of a sudden the signal starts going proper, right? But this period of time, we also call that the transient response, right? Um, and then after the transient response is over, we kind of see that the signal assumes kind of looks like the what we had at the input, but not exactly because we did pass it through a filter, and the filter did something to the signal, and this is what it did. Okay. Um, Now, when we look at the spectrum, and we look at the spectrum down here in the middle, in the bottom middle here, something all of a sudden looks strange, right? If this is some kind of low pass filter, I was expecting uh, the main, right, the fundamental tones, the or frequency components, to go, and maybe the second and the third one, right, to go through. But here you can see they've dropped quite significantly, right? So it was somewhere close to 3.5, or close to 3.5, and then it dropped to like 2.5. That's a significant drop, right? And the same thing with some of the, like the second and the third. Well, actually, this is the um, how do I say this? This is 1 hertz. This is 3 hertz. So this is actually the third and the fifth, right? The even components here are 0. So first, second is 0, third, fourth is 0, and fifth. Okay. And you notice that the third and the fifth are really small. And after that, they're pretty much 0 or highly attenuated. But there's these other components in here that I really don't know. Wait, what did that happen? Why are these here, right? Or they're at least hard to explain. Okay. Well, what's happening here is, remember, we've always done everything for a periodic signal. Turns out that we are analyzing a signal, or the portion of the signal that we're analyzing is not periodic. So in practice, we really never start looking at the output from t equals 0, because we know there's just going to be a transient, and we know there's going to be a delay, and we're not interested in that. So normally in practice, what you do is you throw away, and normally we do it in terms of symbols. So let's say that every 1 and -1 here is a symbol. So let's say we want to throw away the first 4 symbols, right? So we would throw away the first 2 seconds, okay? That's actually in the code. It's just that for now I had commented it out so I can make that quick talk to you guys. And that's what this portion of it is, okay? So let's go ahead and uncomment that, and we'll run it real quick. But the way we do this is, right, um, okay, it starts here. Here's where it's the new signal starts, right? The one where we eliminate the transient. Actually, there's the comment. Eliminate the transient. So we're gonna, instead of doing 0 to 5, we're gonna do 2 to 7, right? So I'm gonna have a new start and a new stop time, right? And I need to figure out where those are. And I'm gonna have a k that's gonna go from there to the stop time now, okay? And we establish our t vector the same way we did before. We calculate the square wave. This is the original square wave. It's just going to go from 0 to 7 instead of 0 to 5. We're going to convolve it with our filter. This is still happening. We're still doing the convolution with the filter and its impulse response, right? And then the new GTD, right, is going to start at N0 start, right, which is what I calculated here. This is the point where we're actually throwing away the first uh, 2 seconds of the signal. This is the point, right? And this is honestly what we do in practice. We sort of ignore the transient. The same thing with t new. I need a new time vector. That's what this means. A gt new vector and a t new vector. And this, okay, is my new signal. I threw that data away, and that I will plot, and then I will do the Fourier transform of the new GTD. Okay. And if we do that, let's go ahead and run that real quick, and let me go find the figure for you guys. Notice now that we have the upper right hand and lower right hand side. Uh, so sure, now our signal looks kind of periodic. It does a little funny thing there at the end. But that's again because we stopped it, right? Had I let the I should have let the simulation run a little bit longer and still truncate it at 7, right? So maybe let it run till 9. So I let the effects of the filter die out. um, gracefully. I did not do that. I actually stopped it. So I have a little bit of a transient at the end. But that doesn't create as much of a problem as it did before because you can notice now the amplitude of my main terms are back, and you can see that at least the third one is looking pretty good, and the fifth one is beginning to drop. That's probably the filter. Now, there's still some few little components in here, and I'm almost willing to bet that that's because I did not let the signal completely die out. But you guys can go and experiment with that, right? And I'll let you guys actually solve that if you have the time and the interest to go do that. Okay, with that, we're back to our slides, and that was honestly all I had for you guys today in this lecture. So until the next one, see you guys soon.